This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on average value of functions. We're going to look at the function f of x is 9 minus x squared on the interval from 0 to 3, and it looks like this. You want to find out what the area under the curve is. That will be the integral from 0 to 3 of this function. That's going to be the first part of our discussion. Of course, the antiderivative would be 9x minus x cubed over 3 evaluated from 0 to 3. Plugging those values in, 9 times 3 minus 3 cubed over 3 minus 9 times 0 minus 0 cubed over 3. This, of course, just becomes 0. 27 minus 27 over 3, that's what 27 minus 9, and we get 18. So the total area under the curve is 18. We're going to use that to find the average value of this function on that interval. So if we had to have one y value to describe this function, what would it be? Well, again, the area under the curve is 18. We've done that. Here's our goal. We want to construct a rectangle on the given interval from 0 to 3 so that the area of the rectangle is the same as the area under the curve. Now, the area under the curve is 18. If the width of my rectangle is 3, what does the height of the rectangle have to be so that the area of the rectangle is 18, that is the same as the area under the curve? Well, area is height times width. The area under the curve is going to be 18. The width is going to be 3 from 0 to 3, or 3 minus 0 on that interval. So that the height is 6, that is the average value of our function. So you can see there's our rectangle. So the area under this orange rectangle is the same as this pink area under the curve. So the average value of the function is 6. And there is some number whose height is 6 on this function. You can see it right here. What is that value? F of what is that average value? Is that 6? That's something we'll be answering later. So again, the height of the rectangle is the average value of the function. And the notation that we use is f with a line on top. So f bar is 6. The average value of the function is 6. And one question I want you to think about is, can you find a number between 0 and 3? Find a value c between 0 and 3, such that f of c is 6. And sure, you can visualize that. And we'll get to that later. Let's look at another example of the average value of a function. We have f of x is sine x on the interval from 0 to pi. So we need to find the area under the curve. Let's visualize it. Let's see it. So from 0 to pi, we have this much area. To find that, we'll take a look at the integral from 0 to pi of sine x dx. The derivative of sine is cosine. The derivative of cosine is minus sine. The integral of sine x is minus cosine, so we're going to evaluate minus cosine from 0 to pi. So it'll be minus cos pi minus cos 0. Cosine of pi is -1. Cosine of 0 is 1. -1 minus 1 is -2. Minus in front, of course, will just be +2. So the area under that curve is 2. Can we find a rectangle on the interval from 0 to pi that will also have an area of 2? That's what we have to ask ourselves. The area under this curve is 2. The width from 0 to pi is pi. What will the height have to be? So 2, the area, is the height times the width of pi. So of course 2 over pi is the height. The height of this rectangle is 2 over pi. The width is pi. 2 over pi is the average value of that function. So let's look at a formula that we can use to determine the average value of a function. So we're starting with this. We know the area under the curve is the same as the area of the rectangle, and the height of the rectangle is the average value. So the area under the curve is the integral from a to b of f of x dx for a function f on the interval from a to b. The area of a rectangle is height times width. Now the height of the rectangle is the average value. The width of the rectangle is just b minus a. We want the area under the curve to be the same as the area of the rectangle. So this integral should be the same as f bar times b minus a. So if that's the case, that integral is f bar times b minus a. To solve for f bar, all we have to do is divide by b minus a. So there's the formula for the average value of a function, but frankly, I think it's better to think of the geometry so that it's meaningful. But we use this average value of a function to develop our mean value theorem for integrals. So let's take a look at that. If a function is continuous on the closed interval from a to b, then there is at least one point c in the interval such that f of c is the average value of the function. So we've looked at our two examples. We could find a point c in either case where f of c was the average value of the function. And there is our formula that we just derived for the average value of the function. Can we find a point c between a and b such that f of c is that average value of the function? So let's look at our first example. We had f of x is 9 minus x squared on the interval from 0 to 3. We said the average value of the function is 6, and I'm claiming that this point right here, where the line that defines the rectangle and the curve meet, is when x is square root of 3 and y is 6. So obviously the y value has to be 6. Can we show that the x value is the square root of 3? So we're looking for a point c between 0 and 3 such that f of c is 6. We want f of c to equal 6. Well, if 9 minus c squared equals 6, then c squared equals 3, which really gives us two answers, doesn't it? We could have c is square root of 3 or c is negative square root of 3. But only one of them is in the interval from 0 to 3. So the c that we want that is going to satisfy the conditions of the mean value theorem for integrals is a c of positive square root of 3. And there you can see it. There's that point. Square root of 3, about 1.7, gives us a y value of 6. So the c value is the x value of the intersection of the line that defines the height of the rectangle and the curve itself. Let's take a look at our example here for f of x is sine x. We said the average value was 2 over pi. So 2 over pi is the height here. I'm going to have a c here that would work and a c here that would work. So this time we should be able to find two c values in the interval from 0 to pi such that f of c is the average value is 2 over pi. So indeed, there's the height. There is the 2 over pi. F of c is 2 over pi, so sine of c equals 2 over pi. Remember, when sine is positive, there is a first quadrant and a second quadrant answer. The first quadrant will be the inverse sine of 2 over pi. And we've approximated that to give me about 0.69. Pi over 3 is about 1, so 0.69 is a little bit more than 2/3 of the way there. So we can see that this dot meets that condition. Our second quadrant answer will be pi minus that 0.6901, or pi minus the inverse sine of 2 over pi, which is 2.4515. So there's our second value c, such that f of c equals the average value of 2 over pi. So the mean value theorem for integrals tells us we have at least one c in the interval, such that f of c is the average value of the function. In this example, we found 2, which is fine. Let's take a look at one more question. We want to demonstrate the mean value theorem for integrals for this function. F of x is x squared plus 4x plus 2 on the interval from 1 to 3. First step, find the area under the curve. Find the integral from 1 to 3 of x squared plus 4x plus 2. Antiderivative x cubed over 3 plus 2x squared plus 2x. Evaluate that from 1 to 3. Plug in 3 first, minus plug in 1 second. 3 cubed over 3 plus 2 times 3 squared plus 2 times 3. Plug in 1 cubed over 3 plus 2 times 1 squared plus 2 times 1. 27 over 3 is 9. 9 times 2 is 18. 2 times 3 is 6. 1/3 plus 2 plus 2. 18 and 9 and 6 gives me 33. 4 1/3 is 13/3. So 33 times 3, 99 minus 13/3 is 86/3. So the area under the curve is 86/3. The area under the curve should be the same as the area of the rectangle, which is height times width. So area under the curve is our 86/3. Area of the rectangle is the height times the width. The height is the average value of the function. The width from 1 to 3, b minus a, 3 minus 1 is just going to give me 2. So we have 86 thirds is f bar, the average value, times 2, which will give me 43 thirds as our average value of this function on the interval from 1 to 3. So if I am going to go ahead and find a value c on that interval, such that f of c equals 43 thirds, we're going to go ahead and plug c into f of x. So f of c is 43 thirds. That'll be c squared plus 4c plus 2 is 43 thirds. And I, of course, should change that to c instead of x. So we have 43 over 3 equals c squared plus 4c plus 2. Multiply both sides by 3. That'll give me 43 is 3c squared plus 12c plus 6. And let's subtract 43 from both sides, which will give me 0 equals 3c squared plus 12c minus 37. Now to do this, we're going to use the quadratic formula. Normally we would say x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. But I have to say c because we're solving for c, so I apologize for using c in two different ways here. But that's what we're working with, and we can go ahead and plug in those values and see what we get. So negative b, negative 12, plus or minus b squared, 12 squared minus 4 times a times 3 times c times negative 37 all over 2a all over 2 times 3. Negative 12 plus or minus 144 plus 444 over 6. We get c as negative 12 plus or minus root 588 over 6. We are looking for a c value between 1 and 3, so we'll need to get approximate values to identify where those numbers are. And we have a c of 2.041 and a c of negative 6.041. So this is not one we want, it's outside of our range, but we did find a c between 1 and 3, between a and b, such that f of c was the average value of the function. And to get a visual of this, choosing the c of 2.041 since that's in our interval, there is the function on the interval from 1 to 3. The area under the curve is 86 thirds. The average value is 43 thirds. That's the height. Notice the width is 2. 43 thirds times 2 is 86 thirds, the area under the curve. And c, just a little bit more than 2. So you can see where this function intersects the height of that rectangle. It's just a little bit more than 2. And that will conclude this lesson.